do his thing, so to speak.
Sure.
Able to stand up the infrastructure, carve off VMs, all that good stuff. All right?
Okay.
So I'm assuming you can see my desktop okay?
Yep.
All right. Well, then let's get rolling. Marketing fluff on the background. Okay. We did formally launch the company in 2008 after a series of discussions ranging from 2006 and 2007. The term hyperconvergence itself, that's actually a term coined by a now retired analyst in Boston.
Okay.
You probably know him. He's been around for forever. Arun Tanaja.
Oh, yeah.
So back in early 2011, we took our early models of HC3. Didn't have a name for it. Didn't really fit the virtualization as it had been known to that point category, right? And said, look, this is what HC3 is. This is what it does. And over the course of that 8-hour meeting, Arun pops up with hyperconvergence. That's what this is, because you're collapsing out, getting rid of all the legacy stacks.
Right.
HC3, the term itself, is actually a poke at EMC, a riff on EMC squared.
Okay.
Okay? You can thank Jeff Reedy for that.
Mm-hmm.
Formally launched at VMworld in 2012. And as an amusing side note, if you ever have the opportunity to design from the ground up a virtual infrastructure, the entire architecture, every single layer, okay? Storage stack, cluster orchestration stuff, management stack, DR stack, the whole bit, okay? And do it without using any VMware code of any kind. And then launch it at VMware's flagship show.
Right.
Do it. It's a whole lot of fun. You won't be asked back at all. But man, that was a whole lot of fun.
So you were there early on, Alan. Huh?
I'm employee number 8.
Oh, wow.
There was 7 founders and 2 sales guys.
Mm-hmm.
One that replaced another that preceded me.
Okay.
So I've been on since nearly day 1. We'll call it day 2.5. Okay.
Good. Mm-hmm.
Now, the concept is incredibly simple and straightforward. Virtualization, as we know it, as we knew it at the time, etc. Answer one question: why is it so complex? Why is it so expensive? Why are there so many moving parts from different vendors that all have to play together? Why does it involve so many people from so many different computing domains, areas of expertise, VCPs and CCNEs and SNIA certified storage engineers? That was the original question we set out to solve. And what we discovered was, well, things are that way because virtualization was never purpose-built. Never. Okay? It started life, if you will, as a science experiment. Now, before I get into that, the vision that we set, as an adjunct to the question, why does virtualization suck? It's got killer apps, but why does it suck to set up? Why is it unreachable for so many? And, well, Scott Loftmiller, one of the other founders here, laid it out so very perfectly, because most of the world out there can really take advantage of virtualization everywhere from now what we call the edge to the SMB to the core to the cloud and all the way through the stack, right?
Yes.
Now, with that being said, I mentioned that what we discovered was virtualization had started life as a science experiment. Could you take the concepts of highly available virtualization from the mainframe space, from the old AS 400s and 390s and 380s that preceded it, and translate that conceptually to the x86 space? And the answer was absolutely. Could be done. Was done. Mid-90s, early to mid-90s. And that took us from here to here. Wow, let's switch colors because yellow is horrible. From here to here.
Yep.
Awesome. Well, suddenly you, instead of having to have one dedicated box per function, right, you could have one box that had 4 or 5 or 6 or 7 different functions. But that brought problems of its own. You know, there was a ton of cost savings, obviously, and a ton of simplification in taking that approach. But one of the immediate problems was the silo of storage problem that was presented. The fact that when that box died, it didn't just take out the file server. It took out file serving and email, and it took out the database and. So to solve that problem very specifically, a technology was borrowed from the highly available database space, shared storage. Originally, if you jump in your Wayback Machine and head back to the early 90s, literally folks were using physical SCSI storage arrays, eliminating the terminators and cabling directly to 2 separate servers. Okay. Fast forward a tiny bit, and you had things like Fiber Channel and real shared storage starting to come out at a block level, and then iSCSI because Fiber Channel was wicked expensive, unapproachable. And then, of course, you got the repurposed file shares, your filers, your NetApp boxes, your SMB shares, etc. Well, that solved the silo of storage problem. It's repurposed technology, storage protocols and all, but it eliminated the cost savings. Suddenly you had to have network guys involved, virtualization specialists involved. You had to have storage specialists involved. Well, that doesn't sound great until you realize that that's what created the killer app for virtualization. Live migration, fault tolerance, HA. None of that had realistically existed in the x86 space prior. Okay? Well, as we move forward from that point, you start seeing that killer app and that high availability and fault tolerance really running to the fore. And man, for the Fortune 50, the Fortune 500, hell, even the Fortune 2000, that became table stakes. And then it starts to sprawl into what we see leading in to founding scale. Okay. Well, for us, what we wanted to do was take those concepts of highly available virtualization, those killer apps, but take a clean sheet of paper approach to how it should have been done in the first place. Okay?
Mm-hmm.
Now, the first question we asked ourselves, that legacy inverted pyramid of doom, the servers plus switches plus somebody's SAN plus somebody else's hypervisor plus somebody else's DR stack, etc. Is that the path that should have been followed in the first place? Oh, and layer in storage protocols of various types and vendors and how well they may or may not play with those standards, etc. The answer for us was, oh, dear God, no. Start with an active cluster of self-aware nodes. So we did. And we had a series of additional goals on top of preserving the killer app, high availability, fault tolerance. Simplification everywhere. Automation everywhere. Focus the product on being easy to set up, easy to grow, easy to manage, inherently have the ability to lose any component anywhere at any time and everything just keeps going, And equally, if not more importantly, ship a product to the people that need it most, whose budgets aren't categorized in the tens or hundreds of millions. In other words, don't ship a product at a 1,600% price premium over the cost of the gear that it comes on. Okay?
Mm-hmm.
Now, we can talk very specifically about things like this. You know, the fact that there's no VMware, that it's an all-inclusive architecture. But I think it might be a bit more useful to, from a technical perspective, dive directly into what an HC3 cluster really is.
No, I think that makes sense. Yep.
Okay. So originally, an HC3 cluster started life as a series of 1U commodity x64 server nodes. Now, over the years in between then and now, that has changed both down and up, running on things as small as the Intel NUC, running on things as large as the Google Cloud Platform, GCP, and everywhere in between. Okay? But the stack is the same regardless of what it's running on. So let's do this. Cluster starts life as that series of nodes sized for a given use case. Ships, shows up on a customer loading dock. Take it out of the box, already layered onto a small partition on drive 1 of every node is a copy of our OS, HyperCore. It is a Linux derivative that has been hardened within an inch of its life. Everything that doesn't need to be there, removed. Everything that does need to be there, done directly on bare metal. Okay?
Mm-hmm.
Now, that partition mirrored onto an identical partition on every other drive on the node. Tiny footprint, okay? A few gig. Doesn't need to be gigantic. Now, the interesting thing about HyperCore is it contains every single layer of the solution done directly on bare metal. From a comparative perspective, if you take a look at, you know, what everybody plus brother plus dog that glommed onto the term hyperconverged, Nutanix, SimpliVity, Pivot3, Maxta, so on and so forth ad nauseum. And honestly, I'm pretty sure I saw a hyperconverged toaster the other day. Unlike those guys, where they took and collapsed the legacy storage stack by rewriting it as a Java virtual machine, embedding that in an actual virtual machine, and then stomping a copy of a full-blown SAN onto each node in their cluster, right? We didn't. Everything is directly in HyperCore. I'll get to that more in a second. Now, first big difference I want you to notice is actually something that isn't there. Notice you don't see a vCenter server or a System Center virtual machine manager or a Rev manager. You don't see a mother-in-law server of any kind. The reason why is we don't need one. You know, fun story. Back when we were in the original development cycle here, you know, we're up back hammering away on code, and I hear my next door neighbor banging away, beating something all to hell in his backyard. And in that moment, it struck me that if I were to follow the legacy virtualization approach to figuring out what my noisy neighbor was up to, I literally would have had to go inside, sit down at my desk, pen a letter to his mother in Cleveland, mail it to her, wait for her to reach out to him, get a response from him, and get back to me. Or I could do what we do.
Just ask him.
Ask him. Lean over the fence and talk to your neighbor. So to facilitate that, we borrowed a concept from, well, that and many other things. We borrowed a concept from the supercompute space, the HPC space, called state machines. It's a series of multi-threaded demonized chunks of code that run as part of HyperCore on every node in the cluster. Now, what those state machines do is both complex and very simple all at the same time. Essentially, what they're doing is, A, establishing what kind of node they're on and what the hardware is, all the way down to the chipset level, to the revision of firmware on the various chipsets. B, the state of all that hardware. What's going on in real time with it from a runtime perspective, from a hardware state perspective, etc. C, track the state of the workloads. Which VMs are running in CPU and RAM at what load levels, at what performance levels, etc. Essentially, there's a state machine on each node tracking every single thing that's going on the node it's running on. Okay? Now, we didn't stop at observation. Okay? We're not a dental monitor. We're a dentist, to borrow a phrase from that TV commercial. Okay? We took the time with the state machine, since we always know exactly what the hardware is, to build in all of the if you see this, do that, all of the OODA loops, if you will, so that not only does it see, hey, that SCSI write CDB to drive 3 just failed, it knows when to retry that write, when to reset the drive, when to reset the controller, when to send the write somewhere else, when to drop the drive, when to drop the entire node. It's when it sees signs of drops and retransmits and link issues and signs of next or fexed, it knows when to drop the NIC connection for the LAN and pop over to its partner, and so on and so forth. Okay? Now, notice the backplane switch here. This can be a VLAN off existing switching, it can be a dedicated switch, dual redundant dedicated switches, can be gigabit, can be 10 gig, does not matter.
Do you intelligently manage the switch, or you don't care? These are just ports.
We don't care. It's just ports. It's layer 2 unrouted, just for the nodes to talk to each other. Okay? What that's used for is those state machines talk to each other in real time, so that every node knows everything going on every other node as it happens, without needing to send a letter to a mother in Cleveland, so to speak, completely getting rid of that entire legacy piece of the pie. Make sense so far?
It does. Complete.
Now, before we even get to the storage stack, what you've got at just this level is a self-aware, self-healing, self-load balancing cluster that stands itself up in about 18 minutes. Nodes out of the box, into the rack, cable up the Cat6 or the SFPs, hook up a KVM to the VGA port, USB port, hit the power button. It asks for what is its IPs, LAN and backplane. Hand them out, hit the initialize cluster button, go grab yourself a cup of coffee or a Mountain Dew or a Jack and Coke if it's late on a Friday, whatever.
And it will load back. It will do the balancing across all 200 nodes, or is there a smaller set that I can that I have to leverage?
Sure. So it goes and initializes the cluster based on how many nodes are in it. State machines discover, hey, this is what my hardware is. Then they go and say, hey, these are the other partner nodes in my cluster.
Got it.
Okay? Now, here's where things get very, very different. One of the first things you'll find is we don't use storage protocols at all. There is no initiators. There are no targets. We don't need them. We wrote our own storage stack, purely block-level stuff from the ground up. It's called Scribe. So when you power up the nodes, give them IPs, hit that initialize cluster button, state machine goes out, discovers what kind of node it's got, what type and how many drives. It then signals a process called Scribe, okay, which is an acronym for something that I don't even recall what it stands for. But essentially, it's our block-level data management engine. Scribe goes out, discovers every single block device of every type in every node in the cluster, fully enumerates the block and cylinder counts of all of the drives in all of the nodes, creating a cluster map, if you will, of blocks, almost like a global namespace of disk, which it then goes and subdivides based on the types of drives it finds, putting all of, say, the SSDs into one tier, all of the NVMe drives into another tier, all of the spinners into another tier. With me so far?
I am.
Okay. Now, the way Scribe works is simple. It pairs different blocks from different drives on different nodes to create a construct known as a reliable block. Bear in mind, we're not even playing at the block device level. We're all the way down at the individual block level, low-level drive control, okay? So we take, say, block 1, drive 1, node 1, block 1, drive 1, node 2. We pair those in metadata to create a reliable block, okay? Just as a metadata construct.
And did you say that spans nodes or can span nodes?
It always spans nodes.
Always spans nodes. Okay.
Minimum 2 separate copies of every block of data on 2 different drives on 2 different nodes in the cluster. Now, their placement's dynamic. The state machines and scribe will shift them around to compensate for node failure, drive failure, node add, hot spotting, load balancing, all that cool stuff. Okay? Now, that reliable block gets associated with a RAM address. When you create a virtual hard drive for a VM using libaio, we literally pool those RAM addresses, hand them directly, again, via libaio, to the individual virtual machine as a local block device. So your entire I/O path is VM sends write to RAM, tees, forks, flushes to 2 separate drives on 2 separate nodes. 3 hops total. Period. Full stop. Now, as I mentioned just a millisecond ago, the state machines work hand in glove with Scribe to automate the entire disk subsystem as well, the entire I/O subsystem. There are no LUNs to create or manage. There are no protocols or protocol overhead leveraged here. We don't need it. Okay? Now, I'm going to jump ahead a little bit, and then I'm going to jump back, because I think it'll lend some clarity to why we're doing things the way we are. Okay. And then we can tie this into some of the edge use cases, all of that kind of stuff. Okay? Let's think about what almost everybody else is still doing in one way or another, and has been the standard for 2 decades. When you wanted to build out a virtual infrastructure, step 1 was always source yourself a shared storage platform, a SAN, a NAS, whatever. Okay? And for the purposes of this discussion, it doesn't even really matter whose. It could be a NetApp box, an EqualLogic box, left-hand cluster, an EMC, VNX, VNXE, Clarion, Celery, Symmetrix, an IBM Shark. Have a good time. Doesn't really matter whose. You'd bring that guy in. Based on what you projected your workloads to be, you'd carve your RAID sets, your protection space, your snapshot space. Okay? Second you did that, the controller for the SAN device layered a file system directly across the top of those RAID sets. You know, with NetApp, it's Waffle. With Isilon, it's OneFS. With EMC, it's either one of the NTFS derivatives or that one they inherited a few years back with their acquisition. With left-hand, it's GlobalDB. With so on and so forth. With IBM, it's pretty much anything from IBM ever. It's GPFS. Okay? Now, you don't interact with that file system much, but A, it's the resource hog, and B, it's where all the advanced feature functionality of SAN essentially lives. Your next step was bringing in your dual redundant switching fabric, okay? Setting up for, fiber if you're going that route, iSCSI if you're going that route. Bringing in the mother-in-law server, whether, if it's physical or if you're going the virtual route, you'd bring in the hypervisor hosts and then carve off the mother-in-law server on them. Welcome to the end of day 3, historically speaking. Next step, you'd start creating your LUNs. We'll just pick on iSCSI here, but it's an interchangeable concept across the board. You'd start creating your storage LUNs so that you could have data stores and homes for virtual machines, etc. But the one question everybody forgot to ask themselves is, what exactly is a LUN from a CS perspective? It's an empty file. It's a sparse file. It's an object file, sitting on a file system, sitting on a RAID set, that gets linked through a named pipe back to the iSCSI target code, running on the SAN itself and shipped out across the network fabric as air quotes block devices to each of the individual hypervisor hosts initiators, right?
Yep.
Or to their fiber controllers. Doesn't matter. It's all the same stuff. Now, when you present ESX or Hyper-V or Rev or Zen or any of them with a block device like that, air quotes block device, they want to create a construct that we'll pick on VMware for terminology standardization's sake, called a data store. But ask yourself the same question. What actually is a data store? It's a sparse file. It's an empty file. It's an object file stamped on top of that block device. And to complete its construction, there's another file system, VMFS, or NTFS if we're talking about Microsoft, or EXT2 or EXT3 or EXT4, or, God help you, ReasorFS if you're in a bad mood in the Linux world. Now, at this point, you're finally ready to start creating your virtual machines. First step in creating any virtual machine is creating the virtual hard drives. You know that.
Yes.
The VMDKs, the VHDs, VHDXs, QCOW2s, so on and so forth. But what are they? They're sparse files. They're empty files. They're object files sitting on a file system, sitting on an object file, mapped across network fabric, sitting on an object file, sitting on a file system, sitting on a RAID set.
Yes.
Then you start installing your OSs. What's the first thing that happens when you install Windows or Linux or, pick your poison? I'll give you a hint. The initials are NTFS.
Right. He creates some partitions. Yep.
Yeah, partitions and file systems. Stop and think about this. This is not only the legacy approach, but is essentially the same approach that's leveraged in the VSAs and CVMs of the world across the board. I'll get more into that in a second. Okay? But you've got an open file, a Word doc, we'll say, sitting in this virtual machine. You want to change a period to a comma. You're dealing with an open file, sitting on a file system, sitting on an object file, sitting on another file system, sitting on yet another object file mapped across a network fabric on top of the overhead of IP and storage protocols, down to yet another object file, sitting on yet another file system, sitting on a RAID set. That's 7 hops coordinated through, what, 3, 4 different kernels each way?
Yeah.
That is not what you call a paragon of efficiency. Never was. This is what happens when you repurpose other people's technology rather than building your own from the ground up. What we did is simple. In the spirit of perfection is not attained when there's nothing left to add, but rather nothing left to remove while maintaining all functionality. Essentially, we got rid of everything that should never have been there in the first place, put the remainder exactly where it should have been all along. Notice the only object file there is the virtual hard drive, and it's not even a file. It's pure block level. The only file system is the one in the virtual machine itself. Doing that same changing a period to a comma, 1 hop, next node over, done. Starting to make a little bit of sense as far as what you're looking at, high level?
Makes total sense, yes.
Now, let's do some quick comparison stuff, because I really want you guys to have a full understanding of my perspective, right? Because I think that'll help you. The other guys, Nutanix, SimpliVity, Pivot3, Maxta, everybody plus brother plus dog that runs a virtual SAN appliance approach, the VSA-based approach is what I call it. Whether you're talking about, the individual storage VMs, controller VMs, in an OmniCube federation, or the CVMs in a Nutanix implementation, does not matter. They all do this exact same thing. Essentially, what they did was they took the entire legacy construct known as SAN, with all of its CPU utilization, all of its storage protocol overhead. And Steve, stop for a second and think about this. I don't care whose SAN we're talking about, right? Don't care whose. You go rip the lid off a NetApp box or an EMC box, a Symmetrix or Symmetri, or however you make that plural. You go rip the lid off of any of those platforms, and inside you're going to find a pile of cores and pile of RAM that exists to do nothing more than handle the overhead of storage management of object files on file systems on object files on file systems.
Oh, sure, yeah.
Right?
Yes.
So what those guys collectively did was they actually took that entire SAN construct, rewrote it as a Java virtual machine to leverage disks inside a box. Then embedded that Java virtual machine, their shiny new JVM, into an actual virtual machine with all of its resource consumption and overhead, and stomped a copy of it onto every single node in their architecture. That's everybody else, with the sole exception of VMware. I'll circle back to that in a minute. Now, you remember all the rules about things like RAID penalties.
Sure.
And you remember the hops conversation we just had. Understand that that series of hops is actually happening inside the box in every one of these nodes. So we'll take that same, I've got a VM, a Word doc, change a period to a comma. Open file, file system, transition the change request down to the hypervisor, which transitions it over to the VSA, the CVM, etc. Up through SSD and flash used primarily as a caching mechanism and its sitting file system, transition down to, via storage protocols internal to the box, down to an underlying file system sitting on top of an erasure-coded disk subsystem. Erasure coding, I define it as essentially software RAID 5, software RAID 6 with some jinky parity options. You remember the RAID penalty rules about that, okay? Yes. Makes its commit, transitions that back, but it's replication factor 2 because you don't want to lose the box and lose your data. So before it makes an exit 0 back to the VM, it transitions at the hypervisor level over across the network fabric to the next node over. Wash, rinse, repeat. Depending on whose platform you're talking about, just at a I/O level before you start factoring penalty, you're currently sitting at between 12 and 16 hops to do something as simple as a single data change, changing a period to a comma. Now, we'll take simple RAID 5, although with erasure coding, that could be RAID 6, that could be RAID 60, so on and so forth, at that underlying level. What's the RAID penalty on changing a block of data? We'll do a RAID 5 for math simplicity's sake.
Right. You tell me.
Read in existing data. That's one IO. That's one IO. Read in existing parity. That's 2. Calculate new parity. That's 3. Write new data. That's 4. Write new parity. That's 5. God help you if it's 50, RAID 50, or RAID 6, or RAID 60, then you double up on the parity stripes and double up on the mirroring in the IO. So you just took a 5-to-1 IOPS hit here. Only you did it twice. So on top of, split the middle, call it 14 data hops, you've got a RAID penalty net effective of, what, 10 baseline?
Yeah.
That's what everybody running a VSA does every day. There's a reason that they've used Flash for as long as they have. They have to. They're essentially using Flash as a caching mechanism to hide a storage subsystem that's performance is best described as glacial. You remember the dust-up a few years back between Nutanix and Storage Review?
I don't, actually. What was that?
You can Google it and see what I'm talking about.
I will.
Nutanix lost their minds at the notion of Storage Review providing an actual performance review of their nodes.
I'll look it up. And it was because of the RAID penalty. Okay.
It's because of how they built their architecture in the first place. Now, here's the really fun part. if you turn off everything that makes a VSA interesting to the large enterprise, to real anybody, right? If you turn off N-way replication, if you turn off dedupe and erasure coding, etc., okay, each VSA consumes 24 gig of RAM and 4 cores, just by itself, not available to anything else. As you go through and start flipping on dedupe, as you start flipping on N-way replication, as you start flipping on the features that make them interesting, that number jumps from 24 to 32 to 64. Hell, with SimpliVity, it goes all the way up to 150 gig of RAM per node, and the core count rises as well. Okay? That's that whole SAN inefficiency thing. Now, with Scale, our entire stack, with all features fully enabled, fits in roughly 4 gig of RAM and 1/10 of a single core. What that translates to is on like-for-like hardware, I can run an order of, 20 to 40% more workloads. I literally can run an entire SMB to mid-market data center in the resources those guys require to boot themselves up.
I'm making notes. What did you say about SimpliVity? Did they have a higher burden than others?
Mm-hmm. Hell, I've seen their VSA RAM allocation go as high as 150 gig of RAM per node.
Okay, interesting.
Mine is 4.
I'm not going to quote you on the competitive stuff, but I'm making notes.
No, this isn't about competitive notes or whatnot. This is about transferring information from my head into yours. What you choose to do with it is entirely up to you. But for you to be able to effectively understand the platform you're looking at, you kind of got to know the recipe for the turkey before you can make a real review of it.
Well, yeah, for sure. Okay. I didn't mean to cut you off. Keep on.
No, that's perfectly fine. Now, let me put it to you this way, because this is probably the simplest way to do it. This is how everybody else writes a block of data.
I love that picture.
This is how we do the exact same block of data.
That is awesome.
That really ought to drill it down, so to speak.
I hope you have that picture in your marketing stuff front and center.
I don't know. That's a Marlena call.
Yeah, okay.
But, as far as I'm concerned, competitive-wise,
yeah, I mean, that really illustrates it right there. That's a great
that just lays it right out.
Okay.
Complexity, non-complexity. Self-aware, heavy use of sysadmins. Self-healing-ish. Oh, and by the way, a straight list price versus list price, this is priced about, call it around half of what this is.
Oh, wow, okay.
Seriously, we set our MSP pricing at something like 45% less or so than what equivalent offerings from Nutanix, Dell, etc. ship at.
Okay.
It's back to that not charging a 1,600% price premium over the cost of the hardware it runs on mentality.
Mm-hmm.
Now, you were asking about blocks earlier, so I'm going to run through a couple of quick slides for you, then we'll jump on a running cluster. This may be, and pardon my absolutely horrific PowerPoint animation skills, but this may be the simplest way to get you to see what it is we're doing with data blocks. Node 1, Node 2, Node 3, simple 3-node cluster. The various virtualization layers. The physical disks in the nodes at the bottom. Okay?
Mm-hmm.
Virtual machine wants to write a block of data. Teed and forked. Round robin, chained to clustered. Call it wide striping, if you will.
Sure.
Those blocks are committed to a minimum of 2 separate drives on 2 separate nodes in the cluster. Both copies are used active-active. Their placement is fully dynamic. First responder wins, right? We will shift those blocks around to automatically compensate for component add, component failure, etc. Now, drive goes up in smoke. There is no rebuild times. We simply duplicate from the alternate copies of blocks in real time, replace the drive. We're not going to rebuild it. We just start sending new data to it. Okay? Entire node goes up in smoke. You remember those state machines?
Yes.
They're talking to each other in real time. Node 3 goes up in smoke. Nodes 1 and 2 state machines already know that Node 3's state machine has stopped responding. They start a come back to life timer that says, hey, let's make sure it's not just a congestion issue on that back-end node-to-node subnet. Timer expires. Well, they already know which virtual machines had been running in CPU and RAM on that node. They already have a full copy of all of the data blocks associated with those virtual machines. So all we have to do is start those workloads up on the other nodes. Doesn't matter that in this case you just lost 30% of all of your resources. It's a non-event. Lose any component anywhere at any time and everything just keeps going. Now, let's dive into something fun rather than continue with death by PowerPoint.
Okay, good.
Nodes. Cluster gets sized, shows up on the loading dock, take it out of the box, stick it in the rack. Okay? Cable up your Ethernet, whether it's Cat6 or SFPs or whichever is appropriate. There's 4 NICs on each node, 2 that point at backplane, 2 that point at LAN. Okay? Cable them up, hook up a KVM to the VGA port, USB port on the back of each node, hit the power button. The nodes come online, they ask you exactly one question. What are my IPs? LAN and backplane.
Right.
Hand them out, takes a minute and a half or so per node. When you get to the last node in the cluster, hit the initialize cluster button, disconnect your KVM, go grab a drink, come back about 15 minutes later, you're up. Point a browser at any one of the IPs you just handed out, doesn't matter which, through the state machines, all roads lead to Rome. Log in, drop into the settings tab, supply your environmentals, who's doing what to who for how many cookies, where to send reporting, all of that cool stuff. Jump up here to the user management tab. That's where you set up different roles for different users, etc., and who's allowed to do what. Jump back up here to the media tab. This is the closest thing you'll find to a data store with scale. Just drag and drop ISOs in. Okay. Jump back to the main screen. Bear in mind, at this point, you're all of 18 minutes or so in from when you hit the initialize cluster button. Carve your new VM. Give it a name. Call this one 11 alpha. Give it a functional description if you like. Maybe this will be a new SQL instance. You can tag it in with other similar VMs for bulk operations. Don't have to if you don't want to. It's entirely up to you. If it's a Windows box, tell us, and we slipstream the para-virtualized driver stack in for you. If it's a Linux box, a BSD instance, Solaris x86 instance, any of those System 5 Unix-based OSs, there's nothing to do. Those para-virtualized stacks have been natively in those kernels since about 2007.
Okay. Yeah.
How many cores? How much RAM you want it to have? Here, we'll give this guy 8 gig. How many and what size virtual hard drives? Okay, so let's give this guy, say, a 50 gig C drive, maybe a 75 gig logs drive, and a 500 gig database drive. Tell us which OS to boot from. Here, I'm feeling nostalgic. Let's do an old 2K8R2 instance. Hit create. You're done. That VM has been instantiated through the state machines. Every node knows about it. Its virtual hard drives are just simply pulled from the block pool. Okay?
Yes.
Think thin provisioning without the inchworm effect of go and find more blocks as you start hitting thresholds. It's all just RAM addresses. Okay? Now, when I power this guy up, note I'm currently logged in here on node 2. What happens when I power up a workload? State machines, the one that I'm logged in on, says, hey, this workload's getting ready to start. transmits that message to the state machines on every other node. They go and do a current projected workload analysis, automatically figure out where this thing needs to run. So you don't even have to think about placement. Live migration, trivial. Hit a button. Okay. Console, it's a pop-up window, SSL and HTML5. Okay. Migrations take seconds, not minutes, even in the middle of an OS load. Again, it's a non-event. Think about why you're not dealing with arbitration through a mother-in-law server. You're not having to deal with iSCSI, barbwin, SCSI reserve, SCSI release, any of that stuff. We simply chop the threads on A, engage the threads on B, move the memory state across the back-end node to node subnet, and we're done. It actually takes longer to do it. It's longer to describe it than to do it. Long story made super short. Okay?
Mm-hmm.
Here's where things get interesting. Those virtual hard drives. This particular cluster, this is a smaller cluster. This is last year's models, the 1150. Okay?
Yep.
Notice each node has 3 spinners and an SSD. Remember how we talked about how we don't set those SSDs up as a cache. We don't need to. We use them as God intended SSD and flash to be used, a proper tier. Okay? Here's where that becomes important. Well, your C drive. Probably not a good idea to waste flash or NVMe on things like page file. Come in here, grab the slider, slap it to 0. All rights for that virtual hard drive go exclusively to the spinning disk tier. Okay? Well, then we've got that logs drive. SQL logs can use a bit of flash. Definitely not going to set it to 0. Well, the second you set it to 1 or higher, all rights invert. They go to the flash tier. Okay? We then kick in our heat map driven by a machine intelligence layer that we run on the back end, an AI engine, in Scribe, that starts creating a heat map, categorizing those blocks as hot, warm, cool, and cold, and automatically destaging cooler blocks, restaging warmer blocks. But notice this isn't an off-on switch. This is a slider. And as I slide this up, what I'm actually doing is establishing relative importance for I/O for this virtual machine's virtual hard drive versus every other drive in every VM everywhere in the cluster. So I set this guy to 7. We'll say anything set to 6, 5, 4, 3, 2, or 1 needs to restage its cool or destage its cool and cold stuff before he needs to move anything.
Okay.
Make sense?
It does.
Now, this is the part.
Why does that give me a warning about not resetting every 24 hours or only every 24 hours?
Because one of the marketing guys likes to be uber careful. I do it all the time.
Okay. All right.
Now, here's where things get fun. That 500 gig database drive. Okay?
Yep.
Databases, as we all know, they can use flash. People live and die by response time. So the more of that you leave in the flash tier or the NVMe tier or whichever, the better that's going to respond. The happier user's going to be, the less annoyed the sysadmin's going to be, or the DBAs. Now, I should probably apologize in advance. My engineering staff, great bunch of guys, but they are epic nerds, and they did steal the naming conventions here from Mel Brooks' classic Spaceballs.
Awesome. Oh, good
and
there. Yeah.
In a nod to that classic Spinal Tap, please note,
It
you
goes
actually
to 11.
go to 11. And we've been doing that since long before Elon Musk got a hold of a cluster.
Yeah.
Now, all amusing movie references aside, there's actually a practical purpose to that. We turn off destaging when you set a virtual hard drive to 11, pinning it, the entire workload, in the fastest tier available. Okay? Pinning this entire workload in flash. So what you've got here with a simple slider that a 4-year-old can use is the ability to, all spinners workloads that just don't need it, all flash workloads that absolutely do, and fully automated destaging, restaging, and relative prioritization everywhere in between. But I'm sure you noticed everything was set to 4 by default. We take a cluster-wide view for the guy that doesn't even want to have to think about that, and build what should be where over the course of about 20 minutes of runtime on a cluster-wide basis. Okay, making sense?
Okay, it does.
Now, snapshots, replication, etc. The way our snapshotting mechanism works is actually pretty epic. Since we take low-level control of the block devices, we aren't dealing with object files and file systems and so on and so forth, and we already have a map of what blocks are being used, where, when, why, and how for him, how many cookies, etc. That puts us in the unique position of being able to simply insert a pointer and use a reference count. Okay, so when I want to take a snapshot of a given virtual machine, and here we'll just take one real quick. Give it a random name, doesn't matter what. That literally just inserts a pointer into the scribe instance for this virtual machine, increments a reference count, says, hey, those blocks were this way at this point in time, implements redirect on write so that if a write past the boundary of that pointer comes in, it goes and consumes a different reliable block instead. We actively support and have tested to 6,000 snapshots per virtual machine per virtual hard drive with 0 performance impact. The only additional consumption is driven by your delta change rate and how long you're keeping the snapshots. Now, snapshots, immediately clonable, startable, runnable as linked clone VMs. Also directly accessible. For example, I can take that logs drive here. I can mount it back up to the running VM as a net new drive from a point in time prior to any other virtual machine on the cluster, provided that I'm logged in as a user that's also authorized to do this. Okay. And instantly, that virtual hard drive from that snapshot at that point in time, a new snap is made. So it's not affecting the source snapshot. And that object is connected to the running other VM that I just linked it to. In this case, Windows 7 box. Okay. Go jump in disk management on that thing. It's there. Online it. Have a good time. Do your thing, copy, paste, etc. On top of that snapshot framework, we built in site-to-site replication with bidirectional block tracking, compression, etc. All of your table stakes stuff is there. Site-to-site replication, any HC3 cluster will replicate to any HC3 target to which it has a route. Checksummed and fully bidirectionally tracked, fail over, fail back. It's literally just a click. Okay? Things like dedupe, yeah, it's there. It's table stakes. It's all managed by the state machines. You don't have to even think about it. It's just automated. It's done on a node-by-node basis in idle thread in the background. Okay?
And do you show dedupe statistics to the user?
Yeah, right here. As a matter of fact, if we go to efficiency, dedupe is saved about 28.6 terabytes of space on this cluster. If we jump to one that's pretty wildly over-provisioned, go to the efficiency tab on this guy. Oh, no, wrong cluster. I'm thinking of one that I've got elsewhere. Yeah, you can over-provision to your heart's content. Now, here's a really cool fun fact. Okay? The nodes you add to a cluster have precisely 0 bearing on the nodes already in the cluster. You could have a cluster based on Xeon X3450 quad cores, okay, circa G.W. Bush's last term in office, and add nodes with Sandy Bridge, Ivy Bridge, add nodes with latest, greatest silver, Pearly class stuff, and happily live migrate back and forth between them without need for compatibility modes, etc. That's been inherently part of the product since day one. What that translates to, you buy only what you need.
Yep.
When you need to grow based on the technology of the point in time of the need, not based on the technology of the point in time of original acquisition. Okay?
Yep.
Now, replication. Spent about 3.5 years working with the Google guys to build in the ability to run HC3 nested on GCP at about 98% bare metal performance. Okay? What that does is simple. We implemented a layer 2 VXLAN overlay so that Google instance, that Google-based instance, simply shows up on your local network using your local IP schemes, etc. So that when you need to do a failover from site A to site B, etc., it's literally no more complex than clone start. Okay? For example, I've got a VM running here on this site, and I'm wanting to replicate to a single node over here. All I need to do, clone from the most recent block set, start, no networking changes of any kind. Just built in. Okay, that's all just part of what you get with HC3. Okay. So I've been moving along really, really quickly here. I know there's a ton to cover.
No, this is good pace, right?
You know, one of the high-level takeaways, there's no licensing cost for any feature functionality built into HC3. There's nothing equivalent to Essentials, Essentials Plus, Standard, Standard Enterprise, Enterprise Plus. You know, no cost associated with things like Site Recovery Manager, etc. We build it all in. We don't charge anything extra for it. Always have since day one. You know, long story made short, you don't need to be a specialist. You don't need to be a VCP or a CCNE or a SNIA certified storage engineer, which is why you see us implemented at, you know, edge-based implementations where, you know, grocery stores, oil platforms, etc. Because, you know, face it, a grocery store manager, he is not a technologist by anybody's stretch of the imagination. He's trying to stay on top of inventory and make the 17-year-olds that work there show up.
Right.
This is an infrastructure implemented there at the edge, there at the core, in the SMB, in the distributed enterprise that doesn't require specialists of any kind. Okay. Questions, comments, thoughts, concerns thus far? Things you want to understand better?
No, this makes perfect sense, everything you've done so far. I think what you haven't showed me is how do I spin up a workload? Okay.
So we just created 1.1 alpha, that virtual machine, right?
Yep.
Looking familiar? Long way around the horn is to go through a full install. By and large, I almost never do that. I create a few template virtual machines for myself, right? Those templates can be used as the baseline for VDIs using, you know, connection brokers that do lifecycle management, Parallels, LeoStream, etc. Connect in through my APIs, find the templates, etc. Or in my case, you know, I need a new 2K8R2 instance. Okay, clone, give it a name, start. Spun up, ready to go, done. Started. And that's it. That OS is in, up, running. That VM's created, instantiated. Here in a second, it'll be started and running on the cluster. There it is.
Okay. Beautiful.
It could not be simpler.
Okay. I'm not sure what else to ask. at this point. What I'm going to do you have your manual online or a user guide?
Yeah, all of that stuff is in the partner portal on our website. Okay. The theory of operations doc, how it all works together, etc. Okay.
Okay. So let me spend some time this afternoon going through that stuff, and if I have trouble accessing, I'll give you a call.
Okay.
And then maybe I'll have some more questions for you, and then we'll go from there.
All right. Yeah, from just a high-level technology review perspective, that's the 90,000-foot view on how it all works.
No, this is good. This is the total great orientation, right? I mean, it's good context.
Okay. As long as it makes sense to you, that's what matters. You know.
Yeah, it does. I mean, I played with systems that look a lot like this, so it's coming pretty quick. But let me read through your stuff. I should have done that before the call, but let me read through your stuff, and then I'll come back with more, I'm sure. I'm going to have lots of questions.
Okay.
All right, man.
All right.
Hey,
Sounds good.
Thank you for taking the time.
You bet. Take care, guys.
All right. Bye.